we know that what is meant by fugacity. So the question is how we can calculate fugacity. So in previous lecture, when we talked about molar gaps free energy, we have an example, and in this example we showed how we can calculate molar gaps free energy for different phases, compare them together. So what are the equations we will use in order to calculate the fugacity? So now we have fugacity is related to residual molar gaps free energy. And if you remember from chapter 6, last chapter, that we have residual molar gaps free energy is residual molar enthalpy minus temperature times residual molar entropy. Okay, so this is the relationships we have from chapter 6. And this is what we have from this chapter. Length fugacity coefficient is residual molar gaps free energy divided by RT. So if we integrate the equations we have from chapter 6 with the integration we have like obtained today in one equation here, so we can relate that length of fugacity coefficient as residual enthalpy minus temperature residual entropy divided by RT. And again, chapter 6, we have many equations to calculate residual enthalpy. You have many equations to calculate residual entropy. You can put all of these equations again and you will end up with this equation here. And this is the general equation that we can use in order to calculate fugacity. And similar to chapter 6, if you remember, to calculate residual property, we have an equation with respect to pressure, another equation with respect to molar volume. So still here we have two equations. One equation if we need to integrate with respect to pressure, another equation if we need to integrate with respect to molar volume. This is the general equation we can use in order to calculate fugacity. Okay, so this one related to residual molar gaps free energy, and we recall the molar gaps free energy residual equations from chapter 6, put all the equations together in order to end up with this general expression. So again, in order to calculate fugacity, this is the equation we will use, but this equation contains some parameters. So these equations contain the compressibility factor, for example. This equation also can contain molar volume. And what we are trying to do, so the whole idea, we will use this equation, we will substitute in this equation how many times? 2 times. So let's assume we have boiling conditions. Vapor and liquid exist together. So we will use the liquid conditions, substitute in this equation, calculate fugacity for the liquid phase. And this will be 1 time substitution. Then take the vapor conditions, substitute in this equation, calculate fugacity for the vapor phase, and compare fugacity for liquid, fugacity of vapor. If they are the same, so this means these conditions represent phase equilibrium conditions. Okay? So in order to use this equation, we need to find compressibility factor for liquid or compressibility factor for vapor. Molar volume for liquid, molar volume for vapor. Okay? And this is why from this general expression, we can have different forms of equations we can use to calculate fugacity based on the equation of state you will use. So you can use this equation assuming ideal gas behavior, for example, at low pressures, and then you will have Z equal to 1. You will find simple equation to calculate molar volume and substitute in this equation. But if you have real substance, then we need, like, if you remember chapter 6, real equation of states, Van der Waals equation of state, Suave equation of state, Ping-Robinson equation of state. So each of these equations of states can be used here or integrated with this equation in order to be able to solve the problem. So this is why we have this general expression, but from this general expression, we will have 3 other forms to calculate fugacity. One will be, if I substitute in this general expression with Van der Waals equation of state, what will be the equations? If I use Suave equation, I substitute in this general expression with Suave equation, what will be the form that I will use? If I'm using Ping-Robinson equation, especially if I'm using hydrocarbons, for example. If I have hydrocarbons, so Ping-Robinson equation is the best fit for this kind of substances. So if I use Ping-Robinson equation and substitute it in this general expression for fugacity, what will be the expression I can use? So starting from now, just we will see how these expressions will look like. Okay, and then I will give you a summary of the equations at the end. So again, this is the general expression. If we have Van der Waals equation of state, okay, so remove Z, substitute with Van der Waals equation of state. Remove molar volume, substitute with Van der Waals equation of state, and you will end up with this form here. So again, this is the same equation, same expression we are using to calculate fugacity. Only This one, it used van der Waals equation of a state, integrate van der Waals equation of a state with the general expression to give you a form that you can directly substitute in this equation. Here you can see we have parameter A, we have parameter B. If you remember, these are van der Waals parameters, and this will be obtained similar to what we did in chapter 7. Okay. And again, this equation here calculates or contains the compressibility factor. Do you remember how many forms we have for van der Waals equation of a state? 2. One with compressibility factor, one without compressibility factor. So here I used the one that containing the compressibility factor. This is why the final expression contains the compressibility factor. I can use the second form and I can end up with this equation here that is not containing the compressibility factor. So I have two equations I can use to calculate fugacity. These two equations are based on using van der Waals equation of a state. And why we are having two expressions or forms of this equation? Because we originally have two forms of van der Waals equation of a state. One with compressibility factor, one without compressibility factor. So here you will see fugacity expression without Z. And in the previous slide, we see the form that was the compressibility factor. Okay, so now we saw the expressions if we have van der Waals equation of a state. So what if we have Suave equation of a state or Ping-Robinson equation of a state? So this will be the expression of fugacity expression to calculate fugacity if we have Ping-Robinson equation of a state. Okay, and again, in this expression we have two parameters. We have parameter A, we have parameter B. If you remember from chapter 7, we have list of equations we can use to calculate these parameters. So parameter A can be calculated from this one, parameter B can be calculated for this one. Here we have small a parameter, small b parameter, and again we need to use the equations in chapter 7 to calculate this one. And this is the summary of the equations. So these are the three fugacity coefficient expressions. The first one, if you have van der Waals equation of a state. Second one, if you have Ridley-Schwank equation of a state. Third expression, if you have Ping-Robinson equation of a state. So based on the equation of a state that you will use, then the expression will be based on this equation of a state.